So this was a similar example, but the main difference between this example and the one I had for homework number 1, both are prismatic shafts. As you can see, this one is not just simply supported and the loads are between the bearings, but we do have an overhang. And then instead of having forces in simply the Y direction and the Z direction, the forces were applied on the gears at some angle. So basically I had to analyze these forces into a tangential component and an axial component on each of the gears. We still had to analyze the shear moment diagram in both the XY plane and the XZ plane. And if we have any unknown forces like support reactions or tension in the belts like you had in homework 1, you needed to solve for these. Once you have the 2-plane bending moment diagrams, we use these to find a resultant moment diagrams to identify the critical section. And in this case here, I can find the resultant, and please note, when we are finding the resultant moment, we have to be looking at specific points. So I look here and the maximum moment is this minus 6,343. Now this is an MY component that needs to be added to an MZ component. Of course, these are vectors, they have direction. So in order to find 2 rectangular components, in order to define the resultant at MC, I take the square root of the sum of the squares here, which we find it to be 6,750. Now looking at A, I find the resultant of these 2 rectangular components, the 4,149 and the 3,336. When we do that, we find the 5,324. Now, the critical location is obviously at C. The critical location is obviously at C. So finding this MC, knowing that the torque exists, I also find the torque. And please remember, the torque is the moment about the axis of the shaft. So in order to do that, I want to take a tangential component. Now remember, these shafts are going at constant speed, so the torques have to be in equilibrium. So there is a torque coming from A, if A is the input, and then B is the driven. So the input from A must be equal to the resistance I'm getting at B, if B is the driven, or the other way around. So if I'm calculate the torque at A or torque at B, they should be equal. And simply the torque extends between A and B. So what we're doing here, if I find the tangential component, 300-pound force would be cosine 20, that would give me the tangential component. If I take this tangential component, multiply it by the radius of the gear here, which will be 10 inches, because the diameter is 20 inches, I should be able to get the torque. This should be equal to FB cosine 20 multiplied by 4 inches. So obviously, FB is a force that has a higher magnitude than the 300-pound force. So that was the first step when we found FB. FB is 750-pound force, which you had to do the same in homework 1 by finding the tension that was not given in the shaft. After that, you are simply using the solid mechanics equations that were customized for a circular section to find the bending axial stress sigma, the torsional shear stress tau, using the equations. Now, what happens here is we substitute it specifically for a circular section. So we're using the diameter. I find sigma and tau. These are specifically, stresses is always calculated at a point. And this point is on the outside or the circumference of the shaft at that critical section at C. So I can simply show that on a stress element. I can show my stresses. So I can come here and show on the stress element that I do have a sigma like this, and I also have a tau force. These are acting at a point like this. And of course, I complete my stress elements, where this would be my 35.2. And this would be my, oops, this is wrong here. It should be going complementary sheet. So here we do have this shear of 7.35. So if you look at this, this is a stress element similar to the ones you've seen in solid mechanics and intro to machine design. At that point, I can find the principal stress. So use the principal stress equation, sigma 1 and sigma 2. I can also find tau max, or you can plot a Mohr circle and find sigma 1, sigma 2, and tau max. So this was a stress analysis. I'm going to skip the deflection part because you don't have to worry about this in homework 3. I know I'm starting earlier, but I want you really to realize the difference between homework 3 and homework 1. And with finding the stress, you can use the static failure theory to find a design factor N, and also use what you learned in fatigue to find the design factor for fatigue NF. And please note that we have to use the Goodman equation because we do have combined stresses. Not only do I have a sigma, but I also have a sigma tau. And this is not, it's a combined stresses, and we have a static or a steady torsional shear stress. When I looked at the stresses in terms of fatigue, it is important to note that as the shaft rotates and the stress, the bending axial stress is going to alternate between tensile stress and compressive stresses. So it is kind of completely reversed where sigma m is a 0, while the torsional shear stress is always the same. I hope that everyone can see this part because this is an important part. Does everyone understand where these are coming from? If you have any question, please feel free to put it on the chat or speak up, unmute your mic and speak up, please. Does everyone understand where this is coming from? Again, this is an opportunity for us to interact, so I'm expecting questions, and I'm willing to go as far as homework 1 or solids or intro to machine design to make sure everyone is up to speed. Does everyone see where this step is coming from?
Hi, Professor. Can you just go over that real quick?
Of course, of course. All right, so let me switch here to my notepads. So we do have a circular shaft like this, and this is the center. So if I look at the maximum bending moment, now we're going to get this in one direction. Yes, I understand we do have a Z component, an MZ, and we also have an MY. Now between these, we find the resultant bending moment. So I'm gonna make up something. Let's say the resultant bending moment that we find, and in this case, we found that the maximum was 6,000 and some, and we found that to be at point C. So let's say our MC is going in this direction. With that being said, if this is the direction of MC And since this is the circular section, the neutral axis is going to be along the axis where the bending moment acts. And if I say that, then perpendicular to that, this is where I'll be getting my maximum tensile and maximum so this is my moment, right-hand rule. I get here like maximum tension, sigma T max, and here I'll get sigma C max. Right? So this is the axial stress from MC. Now, if I plot the axial stress distribution here, I'll be looking at variation along this perpendicular direction. That is going to look like, here is my maximum tension, and here is my maximum compression. And at the neutral axis, I have a zero stress. So I'm looking like this. So this is sigma T max, and this is sigma C max. We're all good so far? Okay. Now, as the shaft, now this is good if this was a static loading. And it is, while the load is not changing, the forces are not changing, the forces applied on the gears are not changing, the shaft itself goes through rotation. So what happens when the shaft goes through rotation? And let's follow that. And it's going rotating at a constant speed. I'm starting, if I pick on this point that has the maximum tension, and let me look at the plot of the variation of the axial stress over time. So this is here time, and here this is sigma, and specifically I'm looking at this point of the shaft. So this point starts with a maximum tensile stress. Now, as the shaft goes 45 degrees, what's going to happen? It's going to move to the neutral axis. So the stress will continue to decrease until it becomes a zero. So I get this. And then as it continues to rotate again, I get another 45-degree angle. It will become negative compression until it gets to the sigma C max. So here I have sigma C max. And so on. It moves another 45-degree angle. It goes back to the neutral axis. It goes to zero. Continues back to its original position to make it 360 degrees. It comes back to sigma tau max. And of course, this curve will continue as the shaft continues to rotate over time. You all see that? Now, looking at this, I can clearly say that in terms of fatigue, if I identify the most important parameters, sigma A, the alternating stress, and sigma M, it becomes obvious that sigma M is zero, and sigma A is equal to sigma max. Can use the comma. So this is where I get my sigma A and sigma M in regards to the axial stress. Does that clarify it?
Yes, thank you.
Very good. I also should do the same in regards to the torsional shear stress, right? So now if I look at the torsional shear stress, so this is here, this is in regards to the bending axial stress on a rotating shaft. Let me do the same for torsional shear stress on the rotating shaft. So again, I have my circular shaft. And we do have this torque being applied. So I do have a torque along its axis. Now what happens when we have a torque on a circular section? We do have, I can write my equation, tau from solid mechanics is equal to T over J multiplied by rho, where rho is the radial distance. Rho is measured from the center through the circumference. Now, clearly, T is constant, J is constant, but R is the one that changes along the cross section. With that being said, I can say then that tau max is equal to T over J multiplied by the radius or the maximum distance of rho that we called it C. So for a circular shaft, I can say that C would be equal to the diameter over 2 or equal to the radius. Since tau is a function of rho, we can say that the shear stress varies linearly in the radial direction. So if I look at the shear stress distribution, I'll be looking at something like this, where here I get my tau max. So I start, if rho equal to 0, right at the center, I have 0, and I get my maximum stress on the circumference. Now what happens as the shaft starts rotating? So the maximum tau acts on the surface. As the shaft rotates, the shear stress remains, this point is still at the surface. So if I start looking at the variation, if I plot here, where I have my tau max, as the shaft rotates, I really see no change in the shear stress over time. From this, I can conclude that tau A is equal to tau max and tau M is equal to, I'm sorry, there is no alternating. Tau A is 0 and tau M is equal to tau max. This is the mid-range or the steady stress. So this is how we can take the bending axial stress and torsional shear stress to find sigma A, sigma M, tau A, and tau M. Okay? So this is where these numbers came from. Now, again, this is a case of a combined stress. So what you have to do here is to find the sigma, the equivalent axial alternating stress, and the equivalent mid-range stress. And in order to do that, we use the distortion energy theory to find an equivalent stress. And since the stresses are in plane, it is simplified and we only have one axial stress component. It is simplified to the square root of the axial stress squared plus 3 shear stress squared. So square root of, maybe I should write this quickly here, because this is an important equation that you're going to see. Sigma prime is equal to the square root of sigma, sigma squared plus 3 tau squared. So this is just to find the equivalent. Now I can apply that 2 times. First time to find sigma prime A, So basically, I'm going to put the alternating stress here. So 3 tau A squared, and then apply it another time to find sigma m prime. So I will have here the sigma m squared plus 3 tau m squared. Now, with the same token, we can also find a sigma prime max. Now, for fatigue, I would need the sigma prime A and sigma prime M to find a fatigue factor. But we also have to check for yield. And this is the sigma prime max that I'm going to use to find the yield design factor, which is, if I apply the distortion energy theory, is just SY, the yield strength, divided by sigma prime max. So this is how we came up with this number. But for a fatigue equation, this is my modified Goodman. And again, please note that here we have stresses and we are just finding a design factor. That's why I call homeworks 1, 2, and 3. These are shaft analysis problems and not shaft design. As we get into homework 4, we are going to be doing a shaft design, which is what we are doing this week. So we use this equation here to find NF.